Okay, welcome to part 4 of the RTC Tools training, the Blue River example optimization. My name is Bernhard Becker from Deltares in the Netherlands and Aachen University. We are now in the second part of this demo, hands-on, working with a simple reservoir model, and we use the software RTC Tools. This is about the operations, the optimizations, and here are some ideas about the operational goals for reservoir management. Here more in general. For example, it's quite common to have a boating range for recreational purpose if it's a reservoir that is used for boating, and our example is such a reservoir. Here you see an illustration. Yeah, this is more the lower end of the boating range. The water levels has dropped very low, and it's hardly, still it's nearly not possible to reach the boats here. In this case, this is more upstream of the reservoir here. The boating range is no longer met. Here you see that all the boats are dry. So here there was not enough water to meet this boating range. Another operational goal that we will use is maximum river discharge. Imagine here this river and the city on the left and right banks. This is all okay, but imagine a flood, then this could cause some damage if the discharge is so high that the flooding starts. So we want to use the reservoir to prevent that the river discharge exceeds the flood stage, flood discharge level. And then we have also minimum flow for aquatic ecology. This is always important in the summer during low flow. Water quality issues and temperature play a role, and if we have a reservoir, we can make sure that we don't let the water fall below a minimum flow. Now a bit more into the math. You already have seen these equations. That's our reservoir equation. You have seen the model schematization. It was basically the reservoir with an inflow, then the outflow, and further downstream we had the river city. And in this case here we don't use any time lags, but it is possible to model the time lag from reservoir outflow to the river as well. We don't do that here for the sake of simplicity. And now the goals. We want to specify an operational range for the reservoir, maximum, minimum volume for boating. We formulate this as volume because we have already learned we have an advantage if it's a linear optimization problem. The second goal is the discharge, minimum and maximum at the river city location. Minimum for water quality and maximum for flood protection. So now we asked RTC Tools to find a control scheme which is Q out over time such that all goals are met as good as possible. The unknown variables are V for the volume and Q out, the reservoir outflow. Control variable is the Q out. And the volume here is a result of that and the inflow. And the conflict is here that the release of water reduces the reservoir volume, so we might fall below the minimum water volume, water level, and the inflow increases the reservoir volume, so maybe we might end up above the maximum volume. And the question is when to release water to meet both goals here as good as possible. We code that in Python, and I will switch to my Python environment here. This is PyCharm. You have more details about the installation in the installation instruction document, and I will walk you through the code here. We look only at the blueriver.py for completeness. Maybe it's a good idea to show you where to find it. We have the files here, the folders input, model output, and now we look in source, and here you have only this blueriver.py, and I have also some other files for some experiments. So there the source code, it's called src for source, it's Python source code, what we mean with it. Yeah, it's not a very huge file, and the most interesting part is here the class blueriver. Blueriver connects by name blueriver to the to this file here. We have seen that before, to the blueriver. So RTC Tools looks for a Modelica file that names which name matches to the Python code, Python file here. So it's both blueriver. It's possible to specify different names, but then this needs an additional rule of code. We just use here same names to have it all consistent. And here this is the basic example for introducing to RTC Tools. Yeah, it's basically now that we just add the goals, and yeah, we need per goal a line of code, and here we say goal G, that's the list of all goals. We append a state range goal with two values here. The Trout Lake V is the time series you want to address, and then we have some figures here. This is the priority and the weighting factor, and then function range. This is the range. This time series, so this parameter may vary in between. The state range goal is defined above. Here it is, and there this contains more explanation. Target min, target max, so we use that for minimum volume and maximum volume. The variable we have already seen here, Trout Lake V, and this connects to the time series that we have defined here. There it is. To be correct, yeah, it must be this one here, this output Trout Lake V, and we have connected that to the reservoir, which has the name Trout Lake here, the reservoir node. There it is, and then its parameter V, volume. So this is how things are connected. And this is something the modeler has to take care of, because we are not that far with RTC Tools, that RTC Tools arrange everything for you. But with some experience and this example, I think you can make a good start. So here's some values. I've the reservoir volume goal for flood control here, and I've also another volume goal for recreation boating. And this works in a similar way, but has different values. So here the minimum is higher and the maximum is lower than in the goal here above. But it also addresses the volume, has priority 2 and 3.5 as a weighting factor, but the function range is the same. The third one is the flow range goal for River City. Here I say should be between 7 and 23 cubic meter per second at location River City with parameter Q, and the priority is 3. So maybe this is enough explanation for the start. Let's go back to my slides here. Some background about goals. Technically, a goal, generic goal, applies on an expression and uses variables. We have seen that, but it can also be a cumulative discharge, an average discharge, derivatives. A state goal, this is what we have seen in this example, applies on a state, a primary variable. So that's the most typical goal for reservoir optimization, discharges or volumes. So we have goal in a generic sense, and more specific, it's a state goal. Every time step we want the volume to be between the min and the max. Goals can be defined as path goals, and this is where the time steps come in, and they will be obeyed if possible, but a deviation from goals is allowed, and that's different to constraints. We arrange goals in priority groups from subsequent optimization runs. Here the keyword is lexicographic goal programming, and the results from the previous goals become constraints for the current priority group, and this has been explained in one of the lectures. Then we have also constraints and bounds. Constraints and bounds restrict the solution space. Constraints are usually expressions. These are, for example, the flow equation. And bounds are limits for optimization variables. If constraints and or bounds cannot be met, the problem is infeasible and you get no result. To illustrate the bounds, I go back to the editor here, open Modelica. This is the definition of a bound. It's already in Modelica. It's here, limits the volume between 0 and this large number here. Alright, next slide. Let's now run the Python code and analyze the result. So we open the blueriver.py. I have already done that, and then we run. And then next step is open the results in a program that's called views. It's see also your installation instructions where you can find it. It's a very helpful tool because I can prepare plots for this training that we don't have to sort that out during the training. And here's a table summary of the goals: flood control, boating, and flow range in River City with priorities 1, 2, and 3. And these 3 are active. And active means, when I go back to the code, that we have them here not commented out. Here are some more goals that are commented out, deactivated for the time being. I use this button here, run. Let's see what's happened. What happens? Yeah, this looks good. Exit code 0. Here's some information about the iterations, and I think this is all okay now. Exit code 1 or -1 would not be good, then there's something wrong, but this looks good. So the next step was to go to the output folder and to open this VSZ file times here's export, and this is it's a plotting program that just reads this file here. You can open it quickly. You have seen the import file, and this is the export file with all the output time series in it. And this is what we are interested in: the Trout Lake V, the volume, turbine flow, spill flow, Q out, reservoir outflow, and River City Q. And I use that data to plot here. And what we see here is the volume over time in the top diagram. And the blue line, that's the volume over time, and the pink lines here illustrate the range for boating. And we have also Vmin and Vmax, volume min and max for the flood protection, and you can see it here. This is the upper limit. Hardly possible to see it, but it's there. We can zoom in, but let's leave it like this for the moment and rather go to the next diagram here: discharge over time at River City. So here we have the discharge over time and the min and the max, and what we can see here is that the discharge exceeds this maximum and also the minimum nearly every year. So this is a 5-year simulation with month time steps, but we have a perfect match with the boating range goal. So this might be not perfectly satisfactory. We now will just modify the code towards a different solution, and this explains how this lexicographic goal programming works and also how weighting factors work. So the idea is to run the following 3 sets and compare the results. So we can put recreation boating to priority 2 and flow range at River City to priority 3. This is what we have. And now let's just flip them. So we give a higher priority for the River City discharge and a lower priority for recreation boating. I've here added some goal numbers to facilitate navigation here. So this number 20 and 30. And all I have to do is just put a 3 here and a 2 there. And then I will run again. Use this. This is a typical error, permission denied. I forgot to close this file. I don't have to save, so I just close it. And of course, RTC Tools cannot write on this file when Excel has opened it. So, but this looks good. I go now to the plotting package views. Use this refresh button, and now we see different results. Here we have a good match. The orange line is within the bounds, but no longer the volume. The range for boating is exceeded here. So this illustrates how the priorities can be specified and how they influence the result. And this also illustrates that we have a conflict here. We cannot meet both goals at the same time, and what happens depends on the priorities that we have specified. So now let's go apply the third solution. Both goals get the same priority, 2, and we have weighting factors that are already defined. I did some experiment with it, and this gives good results. And now we go for a compromised solution. So back to the code. All gets priority 2, and here the weighting factor, I don't know, that should be, I think, 1. Let's see. Again, good exit code 0, and now we have a kind of balanced solution. Can maybe, why not use 5.0 as it was. See what happens. So here we give a bit more emphasis on the discharge at River City, because flood is more dangerous than the benefit of boating maybe. So that's how one could argue. I've compiled here the 3 results into one slide. First was reservoir volume range. This one has a priority over the discharge, and the volume range is fully met. Discharge goal only as good as possible under the given conditions. The discharge on plot 2, this one here, the discharge here has priority over the reservoir volume, and we do meet the discharge goal fully, but not the volume range. And then the compromised solution as shown here. Both conflicting goals are now not fully met, but both are jointly met in a balanced or compromised way. So this is what you can do with RTC Tools, and how RTC Tools can help to compromise or to solve conflicts in water use. I've compiled some tips and tricks in one of the last slides. We have already seen that min and max parameters specify the bounds for a volume or reservoir node. These are also referred to as hard constraints in other publications maybe. If the value cannot be within the bounds, the problem is infeasible. And if you run into such an infeasible problem, it's a good idea to check if the initial conditions, for example, are within these bounds. I've already mentioned the nominal. Here's some more information. This is, has influence on the accuracy of the results. Yeah, how to specify the nominal value, that's always a question that I get. Yeah, there's not a clear answer, but at least something that can help. In an ideal world, from the optimization algorithm perspective, bounds, targets and nominals have the same order of magnitude. So this means that nominal should somehow be in the order of the maximum volume or the volume target, somewhere in that range. And the nominal scale the optimization variables to a similar magnitude. Here the example which I already presented, volumes usually take much larger values than discharge, so they must be scaled internally such that a change in volume has a similar effect on the fulfillment of the goals than a change in discharge. And the path goals. A path goal is a goal on every time step. Path refers to the timeline here, and not note that each time step is implemented as an independent goal. If we cannot satisfy this path goal for one time step, say time step A, this will not have any effect on the time step B, how well it's the goal is satisfied there or not. Typical errors, we have already seen one. I forgot to close the output file. What also happens from time to time, initial conditions, they are specified as incomplete time series, like shown here. These values should be floats, otherwise Python cannot really well deal with that sometimes. This is important for the initial conditions, the incomplete time steps. And then it's very important to use the check model tool in the Open Modelica connection editor. I've already shown that, but it's important to stress that again. Check if the equation system is balanced. If it's not balanced, RTC tools will not run and not produce proper results. Okay, that was a quick introduction in the first optimization task. This was the last slide. Thanks for listening and goodbye.